Let's try to do problem number 7 now. Show that for an integer n, integral 0 to L 2 pi I n x over L dx is equal to 0 for n is not equal to 0 and L for n is equal to 0, and hence establish the orthonormality property. So here L is the size of the box, right? L is the size of your cube, your size of the box, the domain size, and so on. Okay, so let's try to do this problem. Okay, so let's consider n is equal to 0. What happens? You have 0 to L, then you have e to the I 2 pi nx over L dx becomes 0 to L, and it becomes e to the, for n is equal to 0, it becomes e to the 0 dx, which essentially becomes just L, right? Now, if n is not equal to 0, then what you have is 0 to L, e to the 2 pi I n x over L dx. That becomes, okay, L over 2 pi I n, isn't it? And then e to the 2 pi I n x over L going from 0 to L. Okay. What does this give you? So this gives you L, L, this would be small l, right? L over 2 pi I n, and then times, you substitute L, then minus, substitute 0, so you'll have 2 pi, e to the 2 pi I n minus 1. And then this I can split it up as e to the 2 pi I n, and what I'll have is cos 2 pi n plus I sine 2 pi n minus 1, isn't it? So this is going to be 1, this is going to be 0, this is going to be 1, so 1 minus 1, your answer ends up becoming 0. Okay, so that's what you have. So with n is equal to 0 you get L, and with n is not equal to 0 you get 0, right? Now what happens is, if you can use both these equations 1 and 2, so let me take the next page and then consider the orthonormality condition. So I'm considering e to the I kappa dot x and e to the minus I kappa prime dot x. That's what I'm considering, right? Over the domain size L. And then what I'll have is this would be equal to 1 over L cube. Remember, it's a volume average, so it would be equal to 1 over L cube, 0 to L. So I keep shifting it between capital L and small l, sorry about that. So I'll have 1 over L cube, 0 to L, 0 to L, and 0 to L. 3 integrals, right? Because it's a volume integral. And I'll have e to the kappa dot x. So the kappa is a vector here, remember. And e to the I minus I kappa prime dot x. And then I'll have dx1, dx2, and dx3. Volume integral, isn't it? Volume integral. So then in order to simplify my notation, I will just put the capital pi symbol, so that I don't, just like a summation, I'll put a capital pi symbol in order to write the product out, and then I'll have pi j is equal to 1 to 3, and it would be 0 to L here again, e to the I, and then what I'll have from here is e to the kappa naught nj xj and dxj, isn't it? Basically e to the I kappa dot x times e to the minus I kappa prime dot x is written like this, right? And because it is a product, I'm using the pi. So then what happens is, I'll have this 1 over L cube, then I'll have this pi, j is equal to 1 to 3, of course, and then I'll have 0 to L here coming from the top, and what would I have? I would have e to the I, now this kappa naught, I'm going to write it as 2 pi over L, right? Because kappa naught, the smallest wave number, is written as 2 pi over L. So I will have I times 2 pi over L and then nj xj dxj, isn't it? All right. So now here this nj is basically let's write it as small nj minus nj prime, and this is an integer, right? This is an integer. So which means in order to prove the orthonormality property, I'll have e to the I kappa dot x minus e to the times e to the minus I kappa prime dot x. This volume average is basically going to be equal to, what is it going to be equal to? It is going to be equal to, so this is now written in the form that I had earlier. Look at this, 2 pi, so I e to the I 2 pi nx over L. And that's essentially what I have here, e to the I 2 pi nx over L. That's exactly what I have. And then this is going to be equal to 1 if, right, nj is equal to 0. And it is going to be equal to 0 if nj is not equal to 0, isn't it? Because this part I just proved it earlier. So then and this is now, that's how I show the orthonormality condition, isn't it? Is that clear? So here what I have is, I started by looking at the integral itself, right? And then I showed that it is equal to L if n is equal to 0, and it is not equal to, when n is not equal to 0, I showed that it is equal to 0. So essentially I arrive at the same relationship here. So then all I need to show is that this is equal to 1, which it will be, as I proved earlier, when nj is equal to 0, and it is equal to 0 when nj is not equal to 0. Hence, the orthonormality condition is proved. I hope this is clear. Okay. Let's try another problem. Show that the Fourier transform, right? The Fourier transform of del squared g of x, so that's the Laplacian, is equal to minus kappa squared g hat of k, g hat of kappa. So this is like the Fourier transform, right? What I am taking with this operator, it's the Fourier transform operator, if you remember. It's the Fourier transform operator. So when I apply that Fourier transform operator onto a Laplacian, what I get is minus kappa squared g hat of kappa. We have actually used this in some of our derivations in class. This is a way for us to actually prove it. So let's go to the next page. Okay. And then here, this is what I have. So if I'll take my f kappa, okay, and I'll keep calling it k sometimes and kappa, but it's essentially kappa, right? Del squared g of x, that's what I have. Remember, g is a function, it's a spatial variable, it's a function in x, and del squared is basically the Laplacian. So I'm taking a Fourier transform of the Laplacian. And by definition of the Fourier transform, this is what I have. It's basically, so the double derivative, the Laplacian, I'll write it as del squared g. G is a scalar, del xj, isn't it? And by definition of the Fourier transform, it is that function multiplied by e to the minus kappa dot x, and this is it is written as a volume average L. That's how it is written as. Okay, so what I will have is, so then what I do is I take the del xj out, and let's say I write it as, del xj of, and it would be del g del xj, because that's the same thing, right? E to the minus kappa dot x, and then volume average L, right? So here what I'll have is now this one, I can write this as, so let's say I write this as g bar, okay, g bar. Then I can just, so that I have the notation as accordingly, then what I'll have is this will be del g bar del xj, correct, and then minus e to the minus I kappa dot x L, like this, because g bar I'm writing as del g del xj, just another variable, writing it in terms of another variable. Now this I know, if I write this, I'm taking a first derivative, right? A first derivative times e to the minus I kappa dot x. And remember, here all I'm doing is I can take this as I kappa j, isn't it? I kappa j gj bar, right? Because gj is the new variable, gj bar, and then e to the minus I kappa dot x, and then I have an L, right? I kappa j comes out, so I have I kappa j with from the volume average, and then I have gj bar e to the minus I kappa dot x L. Okay, this is essentially what I have. Finally, gj bar, okay, gj bar, what I can write this as is I kappa j, and this now can be written as substitute this back. So then I'll have del g del xj e to the minus I kappa dot x volume average. Now this one again I write it as I kappa j. So I'll have I kappa j multiplied by, here inside I'll have an I kappa j, and then I'll have g of x e to the minus I kappa dot x volume average, isn't it? So now I have this I kappa j again comes out of the volume average, so I'll have I squared kappa j, right? Going to the next page, I'll have I squared kappa j, and then I'll have this g of x e to the minus I kappa dot x L, like this. This is essentially, I squared is minus 1, kappa j is kappa squared, where kappa squared is equal to kappa 1 squared plus kappa 2 squared plus kappa 3 squared, isn't it? Magnitude. It's the magnitude. So I'll have minus kappa squared, and then this part here is the definition of the Fourier transform, g hat of kappa. There you go. That's your answer. I hope this is clear. Let's try the next problem. Let's skip problem 9 and go to problem 10. Problem 9 we'll come back and see if we have time. But then problem 10 we can try to work it out. Show that the Fourier coefficient omega hat of kappa of the vorticity omega is equal to del cross u is omega hat of kappa, which is the Fourier transform of omega x, which is equal to I kappa cross u hat of kappa. Okay, let's see how we can work it out. We know that omega is del cross u. Okay, that's the definition of vorticity. Now, if I take the index notation, then what I have is omega hat, Fourier transform, right? Omega hat I of kappa is equal to fk of omega I of x, isn't it? I'm using index notation. So this is basically a Fourier transform of, and I'm going to use the definition of vorticity, which is basically epsilon ijk in index notation, and it is del j uk, isn't it? It is del j uk. Okay, so essentially omega I of kappa is, okay, here what happens is this is the derivative of uk. Epsilon ijk will come out, right? Epsilon ijk will come out, and I'm taking a Fourier transform on the first derivative. I just did this in the previous problem. When I take the Fourier transform on the first derivative, what I'll get is I kappa j uk. I kappa j uk. So what I'm having is, look at this, epsilon ijk, okay, the I is there, but then that is a complex number, not the index notation I, okay, be careful. So I'll have epsilon ijk kappa j uk, isn't it? So that is essentially I times kappa cross u, isn't it? But again, remember, this is all, I should point out that this is a kappa j uk, this is Fourier transform, right? So kappa cross u of kappa. Kappa is of course a vector. Okay, I kappa cross u. So there you go. That's your answer. That's your answer. I hope this is clear. All you did was you started with the definition of vorticity, then you took a Fourier transform. And by definition of the vorticity in index notation, you will have the epsilon ijk, the alternating tensor. Then you have del j uk, right? Del j uk, and epsilon ijk comes out of the Fourier transform. And then you will just have del j uk is basically, okay, just so that it's clear, from here I can write one more step, epsilon ijk times the Fourier transform of, okay, I should point out that del j uk, I'm using a notation for the derivative here. So essentially it is del uk del xj, huh? And the derivative of this is this one. Okay, so just so that I didn't write this step out, but it's clear, right? Eventually that's how you get I kappa cross u hat of kappa. So I hope that you found this clear. Let's try the next problem. Okay, through the substitutions, ui of x equals, and then you have the summation e to the minus e to the I kappa prime dot x u hat of I of kappa prime is equal to summation kappa prime e to the minus I kappa prime dot x ui star, which is the conjugate, by the way, of kappa prime, and uj of x plus r is kappa e to the I kappa dot x plus r uj hat of kappa. Show that in homogeneous turbulence rij of r is the same as rij of r L, as in volume average. L is the size of the box, and then summation e to the minus I kappa dot r over kappa, and then summation or mean of ui star kappa and uj of kappa. Okay, so let's go to the next page and try to solve it, right? Okay, so if I use the definition of rij of r, okay, that's essentially rij of r volume average, right? And then what I have from here is obviously volume average ui of x times uj of x plus r. Okay, I should point out that this is volume average. Volume average. Okay, now what I can also use is that if I take rij of r and I use the inverse Fourier transform, then what I'm going to have is there is obviously an open volume average, and then each ui I will write it as an inverse Fourier transform. So what I'll end up having is summation kappa prime over kappa prime and e to the I kappa prime dot x, okay, times ui of kappa prime, okay, and that's the first part. And in the second part, as in uj of x plus r, I'll write it as summation over kappa e to the I kappa dot x plus r, isn't it? Because it is x plus r, and then uj over uj of kappa. Okay, so uj hat of kappa, so ui hat of kappa, and then close volume average. Okay, I can take both of the summations out, so I'll have summation, so that is kappa prime kappa, and then volume average of e to the I kappa prime dot x, kappa prime dot x, and here I will also have e to the I kappa dot x plus r, isn't it? And then this is entirely volume average because only that remains in there. And then I can obviously have this ui hat kappa prime and uj hat kappa. Okay, so and this can be in a separate volume average, right? This can be the mean of that. So then what happens is here I will have the summation kappa prime, summation kappa, and here I can write this as e to the I kappa dot r, e to the I kappa dot r, right? And I'll combine the other two and write it as e to the I kappa prime plus kappa dot x, isn't it? I'm combining the other two, volume average, and this term stays as such. I'm not changing anything. So since in the volume average it is independent of R, I'll have the summation, of course, over kappa prime and kappa, and then I'll have e to the I kappa dot R, and then over the volume average of e to the I kappa prime plus kappa dot x, okay, volume average, and then the rest of the term as such. So only this term comes in the volume average, and this right here I can use the orthonormality property, and then so essentially this is over kappa prime and kappa, right? This is 0 when kappa prime is not equal to kappa. Kappa, correct. When it is 0 when kappa prime is not equal to kappa. So what I can do is essentially I can bring this down to a single summation. So it will be of kappa and e to the I kappa dot r, and then in the summation all I'll have is this will only be 1. This will only exist if kappa prime is equal to minus kappa. So then what I'll essentially have is ui of minus kappa, isn't it? ui hat of minus kappa, and then uj hat of kappa. That is all I'll have. Everything else will go to 0. So except, because I just proved the orthonormality property, except when kappa prime is equal to kappa, rest of the terms are going to go to 0. So this is all I'll have. Now, that is the first part of the equation, of the question. Okay, I can go further, and if I use conjugate symmetry, then Rij of R, okay, essentially becomes, okay, look at what happens here. I have ui of minus kappa, right? I can just write that as ui star. So this is over kappa e to the I kappa dot R. Of course, kappa and R are vectors, by the way. And then I'll have just ui star of kappa and uj hat of kappa, ui hat star. That is the conjugate. That is a conjugate. So then this is what I have by using conjugate symmetry. Okay. And then finally, by using the definition of Rij, I can write Rij of R as summation of kappa. Look at this. I have this part here, which is essentially Rij. It is Rij hat of kappa. So I essentially have Rij hat of kappa times e to the I kappa dot R. That's what I have. Hence proven. Right? I have Rij R is equal to, because this part right here is Rij hat of kappa. Okay, so I just put that in there. I hope this is clear. Yes, we started with Rij, we substituted that in physical space, then we took the inverse Fourier transform, grouped it up, and then isolated just the ui of minus kappa, uj hat of kappa, and that essentially we wrote it as a conjugate. Then we went back and wrote it as the definition of Rij in spectral space. In spectral space. So I hope you found this helpful. I hope this was understandable to you. Let's try the next problem. From the definition of Rij of kappa, Rij hat of kappa, which we just showed, show that Rij hat of kappa is greater than or equal to 0 for I is equal to j, and Rii of kappa is greater than or equal to 0. And from conjugate symmetry, show that Rij of kappa is equal to Rji of minus kappa is equal to Rji star of kappa. And from the incompressibility condition, kappa dot u hat of kappa is equal to 0, show that Ki Rij hat of kappa is equal to Kj Rij hat of kappa is equal to 0. Note that all of these properties also apply to the velocity spectrum tensor phi ij kappa. Okay, let's try this. So let's see what happens. Okay, here what we'll do is we'll use the definition of Rij hat of kappa. Okay, and use the definition of Rij hat of kappa and substitute I is equal to j. What do I get? I get Rii of kappa. So it's obviously a spectral space. Rii of kappa is now it is within angle brackets, right? Open angle brackets, and then I'll have ui star because I just derived it. I had it as conjugate ui, so hat, of course, ui star of kappa, and it's a function of time, of course, and then I have ui hat of kappa comma t. Okay, this is always going to be greater than 0. This is always going to be greater than 0. You have a complex number multiplied by the conjugate of the complex number. A plus ib multiplied by a minus ib. You will get a squared plus b squared. Always a number that is greater than or equal to 0. So that is right there. Now, if I start with Rji of minus kappa, if I start with Rji of minus kappa, what do I have? I will have within the angle bracket, I'll have uj star because it is Rji, u hat, right? Uj star of minus kappa, and it's a function of t, of course, and ui hat of kappa. Minus kappa, because it is a function of minus kappa, and close angle bracket. Then this is essentially uj hat of kappa because it's the conjugate of minus kappa is the same as the original. So uj hat times ui star of kappa, that's what it is, right? This is the same as Rij of kappa, isn't it? Rij hat of kappa. It's just flipped, that's it. It's the same as. On the other hand, if I start with Rji star hat, Rji star of kappa, let's see, Rji star of kappa, this one. Then what I have is open angle bracket uj star of kappa multiplied by ui hat of kappa and star of this because it is Rji star. Okay, so then this essentially becomes, now I take a star of it, what does it become? A star of the star, it becomes uj of kappa, right? Uj hat, everything is hat. Uj hat of kappa, and star of ui becomes u hat star of kappa. Close angle bracket. This is the same as Rij of kappa, hat, of course. Okay, so I just proved all of this. Okay, hence proved, right? Now, let me go further. Okay, what I need to show is this part here. Okay, so what I need to show is that. So let me use another page. Let's consider ki of Rij hat of kappa. Ki of Rij hat of kappa. And then what I'll have is the ki will come out because that is not part of the volume integral. And then I'll use the definition of Rij. So I'll have ui star of kappa. Okay, comma t is there, of course. I'm just not writing it just to save notation space. So uj hat of kappa, like this, close angle bracket. Ui star times uj hat, right? Ui hat star times uj hat. Okay, so the first one is a conjugate, the second one is the vice. And then I will have here what I'll do is I will actually take it in, and then what I'll have is kappa I ui hat star of kappa and then uj hat of kappa, like this. Then what do I have? The conjugate can be written as kappa I. Okay, the conjugate can be written as ui hat of minus kappa, isn't it, conjugate, and then uj hat of kappa. Okay, and here what this becomes is, I will write this as, now I want to write this as minus kappa I ui hat of minus kappa, isn't it? And because I included a minus, everything else stays the same, uj of kappa. Because I included a minus, I'll have to include another minus outside. Okay, look at what I'm trying to prove, right? And so then this becomes, okay, this becomes essentially ki rij hat of kappa, then becomes, okay, there'll be a minus, of course, and within the angle bracket, what I'm going to have is, I'm going to use a new variable. So I'm going to write it as ki prime ui hat of kappa prime. So the minus kappa, I wrote it as kappa prime, and then a uj hat of kappa prime. Okay, and because this is kappa prime, it would be minus. And here I will write this as kappa prime ui hat of kappa prime, and then uj hat conjugate of kappa prime, isn't it? Because the minus can be written as just a conjugate. So everything I have written in terms of kappa prime. Okay, well, if think about it, ki. What did I start with? Ki rij of kappa, and I wrote it as ki ui star of kappa and uj hat of kappa, right here. And here I'm writing it as another variable, but it is minus ki prime ui hat of kappa prime, and then uj hat star of kappa prime. So these two are the same. Only difference being the negative sign. Only difference being the negative sign. That is not possible. Both of those are the same. I have obviously changed the variable, and I just did a direct shift to the variable. It just became kappa. It just became kappa prime, isn't it? So then kappa became kappa prime, but the only difference being the negative sign. The only way both of those can be true, because these two are the same. The only way these two can be true is if it is equal to 0. So kappa I rij hat of kappa is equal to 0. That's it. That's the only way it can be 0. That is what we proved here. Okay. Now we just proved that the first term part is equal to 0. The second term, okay, can be proved similarly. So if I take kappa j rij hat of kappa, if I take that, then what I'll have is kappa j, okay, and I'll do the same thing. Within the angle bracket, I'll have ui hat star of kappa times uj hat of kappa, like this, close angle bracket, and then I'll take the kappa j inside, so kappa j ui hat star of kappa, and then uj hat of kappa. Correct? This is what I have. Then essentially, if I put the minus and everything, what I'll essentially have is, so this one I'll group it with this one, not with ui. So then what I'll get is ui star of kappa, and then what I'm getting is, look, I'm getting kappa j uj hat of kappa. This is what I'm getting, right? Kappa j uj hat of kappa. And look at this. I have this is going to be 0. because this is kappa j uj, right? Kappa j uj of kappa. So then this is going to be 0 again, because it's the same as the previous, what I saw previously. It's basically the same thing as what I had previously. That means it is going to be equal to 0. Okay, so I hope you found doing all these problems very helpful. We did a whole bunch of problems. And then this was the tutorial session where we got to do about 10 to 12 problems. In fact, in class we did another set of 24 problems before. So I hope these in excess of 20 problems, 24 problems to be exact, that we did has helped you understand the topic, some of these derivations, some of these concepts. It has helped you understand the topic even better, and I hope this prepares you for the exam as well. Thanks everyone.